Okay, guys, thank you for staying this long. This is not the end, it's the beginning of my talk. I'm really happy to be here. It's great to share this information with you. It's a new topic for me. The reason I volunteered for this work stream is I don't know much about it. So hopefully that means from what I've learned I can share with you, and also it means that it's easier for you guys to engage because I'm being very open about this. I'm a thermals guy. I'm not a signal integrity guy, but I'm becoming one. And you'll see some of that perhaps through the slides. So we have 25 minutes today, lots to talk about, and I'm trying to condense some technical information into this, but as an introduction. This was work done in collaboration with my co-lead from Intel, Kai Wang, who is an expert, thankfully, in signal integrity. And he, as Rolf mentioned, can't be here today, but if you will be joining us in San Jose, then you will probably be meeting him there. And he's been a great collaborator in this community. So getting into the overview, so we'll give an overview of the work stream itself quite quickly, about what it's all about, what it's going to deliver, where we're starting from. But main part of the talk is an introduction to the topic of signal integrity. What is it? Why is it important? And how immersion affects it. And then some, as Rolf persuaded us all to do, to add some call to action comments at the end with handy QR codes that you can scan. Okay, and maybe some time for questions if I do my job well enough. So here we go. So the work stream is new. It's 3 months young. We have 60 plus members already, which is fantastic, a great response from the community. We have strengths in a number of areas that are listed, and which reflects really the community within OCP. What we're looking for, though, and this is maybe a call out to any particular expertise that we have in the room, or people that you know in your networks, and of course you can introduce them, why not? Around optical modes of data communication. It's an important area. I think we touched on that in the materials compatibility overview earlier today. Roadmaps from the OEMs and ODMs on what their data rate requirements and what the protocols they'll be using for data communication going forwards. Some information exists, but you have to go looking for it, and it'd be great to bring it to the community so we can align and set some targets. And then standards and certifications. This is a very regulated, electromagnetic emissions are very regulated, of course, in product development. But any particular standards and certification levels required for hardware or applications would be great to bring into this community call. So this is really where we're coming from in our constitution, a strong group, we're making a strong start. The scope of the work that we're doing is really focused on what's in scope on the left, and what we're not doing is out of scope. Maybe it's easier if I talk about what's out of scope, really, which is we are looking at fluids which are new, straight out of the box, not having spent years at temperature or any materials incompatibility impacts being had, because that brings a whole nother range of issues. So initially we're focused on new materials. We're not looking at specific installation procedures, which may be proprietary to certain solutions because we don't know what problems we're yet looking to solve and what the solutions may be. So anything that's specific about a particular product in procedure terms is out of scope. And any material or any equipment or connectors which are not really appropriate, so maybe they don't meet the fluid specification, or maybe they are wrongly purposed, so things which are not used according to their intended purpose, other than obviously immersion in a liquid, are taken out of scope. But apart from that, there's a lot of things that we'll be focusing on. The breadth is across electrical, communication and optic. It's across hydrocarbon and fluorocarbon fluids. And it's looking at practical methods for making measurements, so testing by physical tests, as well as simulation, and also all of the critical IT components are under scrutiny in this process. And we'll talk about what those components and their classifications are and how they impact signal integrity in immersion. Right, so that's the overview of the work stream, and there's a few more slides towards the end of what our deliverables will be. But I thought we'd spend most of the time today just introducing you to signal integrity. Maybe before I start diving into this, and I've got quite a few things to share with you today, I thought we'd have a bit of a show of hands. So who here is already part of the signal integrity work stream? Can we just have a show of hands? Mostly the front row? Most of the front row. That's great to see. Thanks for your support, guys. Okay, so, and there's a guy taking a picture with his hand up. That doesn't mean he's in the work stream. He just loves the pictures. That's great. Okay, and then how many of you work on a daily basis or maybe have responsibilities in signal integrity? Great, so a few more coming through there. Okay, so, but the majority of you, not so. So have I pitched this right, that you're looking for a bit of an introduction to get a broad view and maybe some depth of understanding of where things go when we immerse hardware in the liquid? Great. Okay, so as you know, or as you may know, data travels along lines within hardware, and it travels in a form that is not digital. It's not ones and zeros moving down this line. It's a wave. So it's converted from binary data to analog data, and then it's transmitted along a line. And the transmission, well, the conversion and the transmission introduces errors in the data. They may be temporal, time-based errors, or amplitude errors. So there's a phase, a time delay, and a maybe need for retiming of the signal between transmission and reception. And the amplitude of the wave is affected because you've got losses of energy as it goes along its journey. The time it takes for it to travel along that line is called the flight time, and the time it takes for the analog signal to go from essentially 0 to 1 is called the transition time. And when those times become close, then you have particular issues with data transmission. And as you might imagine, at high frequency rates of communication, those times do become close or exceed, and you've got a situation where you have to be particularly careful about designing the signal path, the layout of the path relative to other signal sources, and the materials that you introduce, and that's the critical point in bold. The materials that you introduce to that path, either directly or adjacently, interact with that signal. So when a company brings a multi-gigabyte system to market, they will already have gone through a great deal of design, development, and certification work for that, typically in air cooling. And the specifications are very stringent, and the cost of bringing that system to market is very large. The chances of them doing that work again for immersion at this point in the immersion technology go-to-market is fairly low. So we have to understand what design for air-cooled systems will perform like in immersion before we can design it for immersion, which comes later as the business grows. In order to really understand then what the impacts are, there are some basics we have to get to grips with. And those basics, which we're going to talk about today, these next 3 points and my next 3 or so slides, is on the basics of structures that you find in those transmission lines, the properties of the materials, of the multiple materials which are present, and how those structures and properties combine to derive the losses to that signal amplitude and the delay in that signal propagation. So, structures first. On the right, there's some nice pictures. I drew them myself. You can kind of tell because they're not very good, but in basic terms, it shows you what the structures that exist within the along the signal path. The first 2 are really things you'd find on a PCB. So the kind of orangey colours are meant to be copper. I got that right, I guess. And the green is the FR4. So this is the insulator that, and as you can see for a strip line, the signal in the center is surrounded by one material, and you've got ground planes top and bottom making a sandwich. So the signal exists within that space, and you have consistent dielectric materials surrounding the transmission line, which is the key point about strip lines. Microstrips are different. It's kind of half a strip line, but where we have two dielectric materials around the transmission line, so the white space above the microstrip transmission line could be air, or it could be a liquid or fluid or both in two-phase. So that's where you have an opportunity for things to not go quite right, because when you immerse it, you're going to change one of the dielectric properties. Others are sockets, which is where we have a connection between components. These may be exposed to the surrounding fluid or air or not. And then cables. The coaxial cable that I sketched there, you might think that that looks kind of like a strip line, but it's a radial arrangement of a strip line. But what if the cable jacket is semi-permeable? What if the ends of the cable, by capillary action, allow the fluid to enter into that space that is colored green? So they're kind of like microstrips in a way, depending on how they're conceived and how they're assembled and connected. So transmission lines have insulators around them. That can be one or a number of materials. They may be solid, or they may be a gas or liquid. As the signal travels along the strip line, it induces a field. Well, the virtue that it exists is because a field exists in fact, and that's an electrical and a magnetic field. And fields on adjacent transmission lines will interact because their fields may overlap, and other impediments along their path may cause the signals to be attenuated. And the fluid or the solid, those insulators, colored green or white on the screen, are one of the axes for attenuation that we're going to focus on today. So here's a nice picture which shows the field that surrounds the transmission line. You can see that we have some perspective on the image, but what I'd like you to focus on is the magnetic field, because it's easier to see in the image, and it kind of gets smaller and smaller and smaller as you go along the line. So if you imagine that's not just perspective, but actually the strength of that signal is becoming lower and lower and lower. Why is that? Why does that happen? Well, first of all, we don't want that to happen. We want the field to be the same as we move along the transmission line. That's called a transverse electromagnetic mode, or TEM for short, and that's ideal. TEM is ideal, where you only have transverse variations, so the field gets weaker as you go away from the strip line, but it doesn't get weaker as you go along it. That's what we want. So TEM is good. Okay? As the signal moves along the strip line, the insulators polarize. They turn around and look in the direction of the fields that are generated. When they do so, obviously it distorts the material, or it changes their electrical field locally, and some energy is stored. Of course, energy that's stored can be given back again, but that depends on the properties of the material. So this is the first point where we see the fluid properties coming into scope. So the energy is stored by the polarization effect of the fluid turning around and looking in the direction of the fields, and the reduction in the field strength, that those circles that are getting smaller and smaller and smaller as we move along the line, those non-TEM effects, are measured or quantified in terms of the dielectric, the relative permittivity of the fluid, or the dielectric constant of the fluid. That's a number that's relative to a vacuum. For air, it's 1, and we look in a few slides about what the properties of the of the dielectric fluids are. So the storage of energy connects with the dielectric constant. The energy that's lost, so the energy might be stored and given back again, but how much is lost, the friction, if you like, or the inefficiency in the process of polarization and reversion is measured by the loss tangent of the fluid. So how much the energy, the field is reduced, dielectric constant, the energy loss, the attenuation of the signal is related to the loss of tangent. The properties, as you can see on the slide on the left, we have some solid properties for the solid conductors around the strip line. And you can see the dielectric constants are quite high. For FR4, it's 4, and there's other substrate materials that I've shown here for reference. And we have values which for air is 1, and then we have higher values, maybe getting closer to the solid substrate materials for the immersion fluids. The base spec, which we learnt about from Peter earlier, is given here at 2.3. So if the dielectric constant is less than 2.3, we shouldn't get large impacts on the SI for immersion, but that depends on the data rate, and that number might reduce at higher data rates. Loss tangents for air are 0, and there's small values but important values for the immersion fluids. As you can, I've given some examples here, and the OCP spec is also quoted. So a bit of maths here, just for those of you that speak maths. I'm not going to drag you through the equations, don't worry. But basically, you can break down the losses of the signal's amplitude into 4 components, and the first 2 on the top right are really important. The first is the conductivity loss along the copper, which you get in any cable or any transmission line. The impedance of the signal has got this symbol Z, or Z, as I say. And that is affected, definitely affected, by the choice of materials that you immerse the hardware in. So conductivity of energy along the transmission line is one of your insertion loss values. The second is the dielectric loss that we talked about that relates, as has been shown, to tan delta. Both of these are a function of the frequency, and what you'll notice in the graph, the red line is the strip conductivity. That increases with frequency, but what you'll notice is the blue line is insignificant. This is a log axis. So the blue line, which is the dielectric loss, is not significant until we get to higher values of frequency. And as we get above gigahertz frequency rates of data communication, the dielectric losses become very significant, dominant in fact. Not to say that the dielectric choice isn't important below gigahertz frequencies. What we're really saying here is that the tan delta losses, that second property, becomes a critical consideration. So we look at this, and we do tests, and we do calculations for those 4 structures that we talked about. And what we find is that the major impact on performance is really around the change to that Z value, or that Z value, that impedance. Changes when you immerse a fluid, when you immerse hardware into a fluid. That change in the impedance, it might reduce. You'd think, yeah, that's better, less resistance, better performance. Well, no. You've just detuned something that they spent billions of dollars tuning for air. So if we look at the impact of the impedance of that signal, when we go from air, which is shown in blue, to when we immerse it in fluid, which is the other lines, we find that we do have a measurable effect on the impedance of the signal due to immersion relative to air. The effect is small, but it's measurable, and it has an impact because it throws things out of balance. It causes signals to be delayed. It causes the signals to bounce back from the connectors because the impedances aren't matched in the whole circuit now. Taking it from air into fluid changes the impedance, and it's no longer a tuned machine. Yeah? Can we retune it? Sure we can. Can we make better choices by design? Sure we can. But right now we're looking at retuning because we're having to deal with systems that are designed for air in immersion. Okay? So just with some simple maths, you can show quite easily that if the width of the strip line is small relative to the height of the solid substrate, so if W is less than H, when you replace the air with a immersion fluid, you get reduction in the impedance. And depending on the fluid's properties, you get differing levels of reduction in impedance. The grey line is the maximum value of the dielectric constant based on the OCP base spec, and you can see quite significant reduction in impedance. For other fluids, which we talked about in the previous slides, it's less impact, but certainly there's a measurable impact. Same goes when if you were to change the level of impact a fluid has on the impedance also depends on the other dielectrics in the system. Yeah, because there's a sandwich of copper in the middle, solid material, and fluid material above. So the fluid has an impact, but the solid material has an impact. And you can offset the fluid dielectric change from air to liquid by looking at different options for solid substrates. But that's a cost, that's a redevelopment, maybe not the best way to go. So maybe there are some other remedial actions, and there are some tricks that signal integrity engineers and specialists have up their sleeve to tune and to optimize this. But that's hopefully what we'll come to in the work stream. So just focusing on the conduction losses, this shows very quickly and easily that the value of the dielectric constant of the surrounding fluid that we immerse the server in has an impact, a measurable impact, and a fundamental impact on the impedance. So in summary, those two properties, dielectric constant and loss tangent, are key. That's why they're in the fluid spec. And we know that the values need to be controlled, and we know that we have a significant impact on performance, and we're starting to see some correlations to impedance, and we can link that back to the TEM reduction. The properties are different for air and substrate materials. We write specifications for those. It's important that we understand their value because they're liable to create losses to signal amplitude and to change the timing of signals as well. We know that any mismatch in impedance caused by immersion really changes the impedance and causes signals to bounce back and change the timing. So it throws things out of tune, and we have to do things to bring them back into tune. And there's a lot of work to be done on this, but we're starting to develop some understanding of the fundamentals and some methods for making measurements. The type of outputs from the work stream is shown here. We are developing best practices for testing and simulation. We have already identified the two key performance metrics in terms of parameters, and we'll be converting these into figures of merit based on performance. And we understand how the relationship with immersion fluid materials, but we need to look at the degradation factors because, of course, like a lot of properties, they change over time and over use. Guidelines are going to be developed, and one of those areas is particularly around the mitigation options that we have and practical ways to retune those frequencies and those timings. This, of course, is going to result in deliverables. Some of these are going to be updates to and further additions to specifications for fluid properties, but there'll be particular outputs from this work stream which will build on the work that's been done by the community. And if you want to get involved, it's great to get up to speed, and there are some contributions in existing publications in OCP that you can look at. The links are embedded in those titles. And finally, it just remains for me to invite you all to join if you find it's interesting. It's a monthly call. It's on first Tuesday, I believe, at 4 o'clock CET. Looking at Rolf because I hope he remembers, but I think that's right. Could be Monday. We'll check that. We'll check that. Okay, it's on the wiki, which is the first link on the bottom. But anyway, thank you very much for your kind attention. I hope that's been informative and interesting to you, and we may have some time for questions, but thanks for your attention.
So, hey Andy, how's it going? So can you elaborate a little bit more about the mitigation strategies?
Not in detail, because the work stream haven't really got to that stage as of yet. Some of the options, of course, are more costly in terms of replacing materials. There's some methods around introducing cavities which have air entrapped within them. That's a technique that's used for air-cooled systems, and how that might stand up in immersion hasn't yet been tried, at least in the public domain. But yeah, it's about mainly material change. You can route the signal paths differently, but that's mainly around addressing the propagation delay. And again, that's a design change. So it's early days, I would say.
Thank you so much.
Thank you.
Given that most of the rack work that happens inside of a data center is nearly always interconnect between the servers, you end up with a lot of bundling of cables. Does liquid actually have an impact on the alien crosstalk, which is the crosstalk between cables, as opposed to where you put up there the start-off crosstalk? And the other thing is, I didn't notice that you had anything with regards to MPO connectors, which are the fiber interconnects for servers. Is that something that you're also looking at?
Okay, last question first. Yes, on the fiber. But as I said, we need to make a call for the expertise that exists to come forward, because the majority of what we have already is for copper and electrical. Regarding the alien communication between cables, that if they're immersed, then you're going to find some attenuation. But it may be that they're in air, but there could be some further attenuation due to any capillary saturation of liquid within the cable bundles. So it depends is the answer to that one. But if it's in air, then I would imagine that you'd have to analyze the fields to know, and look at the structure of the cables. But immersion cables are liable to have liquids within them, and I'd probably suggest that you started there. Okay, so hopefully that answers your question. Guess that's out of time now, Rolf, so I'll hand it back to you.
Sure, yeah, we've got 1 more minute if there